Okay, so today we'll be just summarizing what the main goals of our project or our department is going to be. And we're basically exploring the connection between tropical geometry and neural networks. Wait, let me just see if I can put this in view mode. That would be much better. What a mess. Right. Okay, cool. Everyone can see, right? Okay. So for our main connection is going to be trying to run machine learning models on edge devices. So what we'll be using to simplify our machine learning models is something called tropical geometry. And these are the list of references that we'll be going through. So we'll start with basically the algebra, what tropical algebra is. Then we're going to study neural networks. Let's see if that's in the next thing. Right. We're going to study neural networks separately, and then we're going to apply them to tropical algebra, or we're going to apply tropical algebra to our neural networks. This will give us a weaker, but a systematically weaker model, rather than just limiting our information or just, cutting short our training. We're going to take an already well or a powerful enough ML that cannot fit on an edge computing device, and we're going to try to simplify that into our neural network. So we're going to learn about neural networks, then we're going to learn about powerful neural networks and how to minimize them. Okay, and these are our references again that you would have seen if I sent on the thing. Now, what is tropical semi-rings or tropical algebra as a whole? So I'll give a gist of it before I start actually teaching the material. So I want two things in your mind, okay? Basically, wherever you see a polynomial, without almost blindly, you're going to apply this one rule, okay? You're going to replace your multiplication with addition, and you're going to replace your addition with the max function. So yeah, addition and multiplication over here, we replace it with minimum and addition, or we replace it with maximum and addition. And this tiny change is what's used in fields like algebraic geometry, where you have really complex polynomials and you want to study how these polynomials interact with each other. And these polynomials can go for very high degrees with variables like x, y, z, omega, and so on. So tropical algebra is used sort of like a simplification tool for algebraic geometry, which is a notoriously difficult field of math. And using this change, we can find things about algebraic geometry, like the number of intersections between any two given polynomials. Now, why do we have to care about neural networks? Neural networks are in some sense really complicated linear models, right? So what we do is these linear models try to capture non-linear relationships between any two given things by minimizing your loss function. So the point of trying to take this same simplification approach is to take your neural model that is highly nonlinear, similar to how things in algebraic geometry were. And we're going to sort of linearize the output. In some sense, we make it weaker. And our goal as a group is to find out just how much of a compromise we have to give. Because we don't want to just put effectively useless LLM on our edge computing device. So first, what we will do, so this is the applications exactly of what we will try to work towards. However, these applications seem mostly far-fetched to me, so I've included them here just in case anyone wants a more technical side of things, and just in case anyone wants to see where it could go. This is where I think it could go, but I don't think it will go that way, because we're probably going to stop the minimizing technique from the neural network. However, this is all coming from a point of view of edge computing. So you and me, neither of us know what edge computing exactly is. We're going to find a way to define what exactly are the limitations of edge computing compared to regular computing. And we're going to try to fit said compromises to the simpler model that our original neural network was. Now, this is also just something I don't exactly know well enough. And so this is our basic goal, right? We're going to apply tropical concepts, and we're going to try to give simpler ML models for our for our edge computing device. The one that I do believe in later on, which I will try to merge with the information theory department, is the study of algebraic security. So a homomorphism is a way to say that you're mapping something from another thing, and the study of encryption that is based on such sort of mappings is called homeomorphic encryption. And so in some sense, the way we took our addition and multiplication, then we converted it to minimum or the addition. These are in some sense a mapping from two operations to another operation. So in the exact same sense, they are homeomorphisms from one type of algebra to the algebra that is called a tropical algebra or a tropical semi-ring. And these things I will make concrete once I start writing. And yeah, I think this is basically the point I wanted to say. The point of this PPT as a whole was to provide references. So with that, I will now start drawing. First, I'll start reading actually, and then we shall draw. Maybe we'll do both. I don't know, I'm indecisive, but okay. This is here and this is here. Okay, great. Now close this. Okay. So we start by understanding what tropical geometry is. Also, another thing, just the general goal, just a comment. The goal is for me to bring you guys on the same page that I am in understanding how to apply this as a project. I personally think that minimizing the neural networks is a good start. However, this should be a completely collaborative study. So, I encourage you guys to find out yourselves, try to teach yourselves, try to, get more knowledge than me on the subject, because I want to keep the prerequisites to a minimum. So if you guys, go ahead and read ahead or just see for yourselves what the rest of the content is. So that is highly encouraged. So you should go ahead and do that. If you find other minimization techniques, that's encouraged. Okay? Can I get a yes from everyone in the chat? Hello.
Yeah.
Thank you.
Yeah.
Cool. All right. Okay. So, we're going to start with what is tropical geometry. And I want you to understand that normal algebra, which is the real numbers with, say, addition or multiplication, has its own interesting properties. And what we were initially interested in the math field was to study the solutions or roots, or more technically what you would call them is the varieties of either an individual or a family of families of polynomials. Now, a lot of you won't know why we even try, and the reason is Everything you see in, say, things like Desmos, let me just admit whoever has joined. Where is it? Yeah, there we go. Where did it go? Oh, why can't I find where the admitting is? Let me just full screen this. Jeez. Okay, it doesn't seem to have anyone waiting. In any case, the recording's there, so they can check it. Okay. So, you've probably seen Desmos or other graphing calculators. Oh, there we go. I heard the thing again. Let's hope the guy stays long enough for me to admit him. There you go. Tanish. Hello, Tanish. We've started our recording, so we haven't missed much, but whatever you have missed, you can just you can just watch the lecture recording when I've uploaded it. Okay?
Okay, no problem.
Okay, cool.
Thank you.
Alright. So, you've seen Desmos and other graphing calculators, and the reason why we care about actually computing these polynomials is because Desmos and many others like it, like say Wolfram, Alpha, what else is there? Wolfram Alpha, just your general calculator, general plotting tools. These are all numerical. So say I gave you the polynomial that looks like x squared minus, I don't know, just a huge number like this, right? And I asked you to calculate its root. If you were to start from the point of the origin and you tried, say, something like Newton's method, right? This graph would only intersect something like that. So say you tried Newton's method and you drew tangents and you went like that continuously. Because this point is so far away, this is an example of something that is not practical. From numerical analysis. So now that I've justified why we use it, I hope it's clear. If you have a question asking why do we do it, please ask. So it's important to understand why we're doing it in the first place. So if you have any questions about we could just do this, we could just do so and so, why would we need to study algebraic geometry as a field? Any questions like that? You can say no if you have no questions. That would be better because I can't see anyone. Is that a no?
Yes. Yeah, I don't think anyone.
Yeah. All right. Cool. Awesome. Okay. So now we're going to get to the tropical algebra part. Oh, not a screenshot. I went delete. There we go. Okay. Right. Okay. So, let's understand how do we go from regular algebra or real algebra. Oh wow, never mind. Real to tropical algebra. Now I brought up polynomials a lot, right? So we're going to use polynomials to construct our way of going from real polynomials that are real, to tropical polynomials. Okay. So I'm going to give you some examples, and then I'm going to give you a question for you to try. It will be a simple question just so I can confirm that you get the idea. Okay. So what we do is, let's just keep a table like this. And I'm going to put this R for real, and I'm going to put this T for tropical. Okay. So if I have A plus B, and when we either have a max version of this thing, that's something I forgot to mention. We're either replacing our addition with a max or replacing our addition with a minimum. Okay. So these are two different kinds of tropical algebras. And in this example, we will be considering max, because effectively these two are equivalent to each other. When things are equivalent to each other, they're only interesting when you start playing with them with each other, you know. So we'll only consider the max version. However, the min version has its own applications. Okay. So like I said, I am going to replace the addition with max. So max of A plus B is max of A comma B. A plus B turns to max of A comma B. Similarly, multiplication gets turned to addition. Let's say we have exponentiation. So exponentiation gets converted to multiplication. Okay. Now, with this in mind, let's just make some more cases like division and roots, just so we have a complete set of tools for attacking any general polynomial. So if I have A minus B, then that is the max of A comma minus B. Similarly, if I have A divided by B, then I have A minus B. And if I have A to the root of B, then I have A by B. Okay. So I'm going to give about 5 seconds, just like have a look, just see if there are any patterns that you notice. And if you do, keep that in your mind, because now we're going to look at some examples. Okay. Just gonna go ahead and scroll completely. There you go. Right. Okay. So now let's look at some examples. Okay. So consider the polynomial ax squared plus bx plus c, right? Our familiar quadratic. And so what we're going to do is we're going to convert it. This is our p of x, polynomial in terms of x, and we're going to apply that conversion from real algebra to tropical algebra, and this is how we denote it. And this is given by, I'm going to start looking term-wise, okay? So first I have A, or no, let me just take a much simpler example. Let me just consider this much for now, okay? So first we have b of x, b into x and c, right? So overall, because there's a multiplication joining these two, I'm going to have a max. Okay. Now on the left side there is no multiplication, so that's going to be c. However, on this side we have b into x. What happens to b into x? It converts into addition. So b into x becomes b plus x. Similarly, now let's consider p of x is equal to ax squared. Okay. And now p of x is going to be basically like finding t a into x into x. Can we agree on that? Yes, right? Excuse me. So these individual multiplications get turned into addition, And so it becomes a plus x, and that is why we get a plus 2x. Now I'm going to combine these two, and I'm going to say p of x is equal to ax square plus bx plus c. And I'm going to do the very dreaded process of scrolling, because this happens to distort my notes all the time, and it's going to kill me someday. Right, okay, there we go. Okay, so now we're going to see what t of p of x is. Okay, so first let's look at simply the addition between these terms. Okay, so that means that this addition I convert into a max. How many terms are there? There are 3. So I'm just going to put 2 commas like this. Now c is the simplest term, so I'm going to put c first. b into x, we talked about it. So the multiplication between b into x becomes b plus x. And we talked about a of x, a of x square, and that gets converted to b a plus 2x. And now I'm going to just ask you to try. Okay, no, I'm not going to ask you to try that one. First, I'm going to say p of x comma y. Now I have 2 variables as a polynomial. Let's say x square plus x cube y plus y square. Now this is going to be one of the kinds of applications that you typically see in tropical algebra. So t of p of x comma y, I will evaluate it now, and next I'm going to give you a similar example so that you can try it yourself. Okay, so again we see the addition between them all, so we have a max. Now we start considering these terms individually. So x square, as we remember, exponentiation becomes multiplication. So 2 into x, or 2x. Similarly, now we consider the second term. First, we know that we see the multiplication sign over here. So whatever this becomes and whatever this becomes, we simply consider this sum of the two, since we're converting our multiplication into addition. So we have something over here, and then we have add, and we have y, since y is simply just itself. Now we have to worry about this other side. Now as we remember, exponentiation becomes multiplication, so we have 3x on this side. And now we consider the last term, which is y square. Again, exponentiation becomes multiplication, so we get 2y over here. Now I'd like to pause and ask if anyone is confused or doesn't understand why any term came, because I'm more than happy to explain it again. And I have a slight doubt that maybe things weren't that clear, that I just said like, oh, do this, do that, and it seems like unmotivated right now. So yeah, any questions, any doubts, any why did you do that? Anything like that? If you say yes, then I'm going to give, if you say that there is no doubt, then I'm going to go ahead and give you another polynomial. And I'm going to give you, say 5 minutes to compute it. And after that, we will move on to the reading. So we will start reading our textbook. Okay?
Yeah, sure. Yeah.
Okay, cool. So, the polynomial I'm going to give you guys is 3 terms now. And I'm going to say x cubed z plus yzx plus, let's give you 4 terms, so it takes some time. X plus yx. Oh, let me just mess around a bit. Why don't you guys try to see what happens when I put x to the power y? Okay, go on. I will wait for 5 minutes for you guys to finish computing this stuff. And then term by term, I'm going to ask what happens. Okay?
Farhan, the last term is not seen.
Oh, the last term is x to the power of y.
No, it's fine.
Okay, so you guys unmute yourselves for now, and I'm going to ask silly questions and you're going to say yes in unison, okay? So, can we all agree that we're going to have a big max on the side?
Yeah.
Awesome. Now, we have 4 terms. No, 5 right now, right?
Yes.
So we're going to have 4 commas like this.
Fine. Yeah.
Okay. Now I'm going to ask you guys to explain these individual terms. So what is the first term, x to the power 3 into z? Anyone can answer. The sooner you answer, the better.
3x plus z.
3x plus z. That's awesome. Correct. Next term, x, y, z.
Y plus z plus x.
Easy. Y plus z plus x. Last term, x. Yes? Next term, x plus y. Last term,
yx into y plus x. Maybe.
y into x. Now another interesting thing I want you guys to note is that if I have a term y commas x to the power of y, or if I have a term y to the power of x.
We are not treating x, y.
We're not treating?
We are not treating like x and y different from natural numbers 1, 2, 3. So I think it should just be a yx, the last term.
Yx, yes, that's true. That's correct. However, we do consider x, comma y, comma z are all real numbers in this case. Okay? What was your doubt? Were you asking if x, y, z are natural numbers?
No, I was just lagging a bit.
I see.
I got it.
Okay, no issue. So, let's assume this is our p of x. This sort of nice looking equation over here. I cut it by accident. But we're going to treat it as though we didn't. Now, one thing I just want you guys to notice, that is if I can scroll by the end of the day because this laptop is lagging. It would be just awesome if this, yeah, there we go, finally. Okay. So, one thing I want you guys to notice is that we have some sort of weird inconsistencies when it comes to polynomials like this. They're not technically polynomials, they're just algebraic equations. Because polynomials are strictly some sort of power to an integer, like how you just mentioned. So, this sort of thing is weirdly out of context, yes? And I just want you to note that this will result in max of xy, comma yx. And since you're taking the max of 2 terms, it's literally itself. Of 2 of the same terms. So, this is some sort of inconsistency, not inconsistency rather. How do you spell inconsistency? 10C. Right. Okay. It is inconsistency, or more specifically, it's a weakness of tropical algebra. Okay. And with that, we are now going to start reading the book. Okay. This should hopefully, everything that I just said during this lecture should hopefully cover about like half of the first chapter, maybe. Okay, so just give me some time. I'm going to put in the huge effort of deleting everything because this OneNote is a pain, a real pain. Oh God. Right. God help me with this app. I can't even do Control All and get everything, which would have been really nice. Okay, great. Okay, so now on the side, I'm going to make notes about whatever we see, and I'm going to just define stuff over here for the rest of today's talk. And when we're done, we will just put a stop to whichever page we're at, and we'll continue from there next time. While we're at it, I'll just go over the index. So let's just quickly go over it, right? The introduction, we will be, basically what we've covered goes up to like 1.3. The rest is about how to actually go from real numbers to tropical numbers, tropical algebras, from real to tropical. And we don't want to go with a discontinuous change, like just replace your multiplication and your addition. We want to go from real numbers to tropical numbers continuously. In some sense, we want to deform this algebra to whatever this algebra is. So, hence why we have things like amoebas and stuff. So these are just formalisms, and it would be helpful to know, because for me personally, I found an application from the definition of amoebas. Next, we will be going more on the application side. And this is where we start applying it to polynomials. Over here, Laurent polynomials is not very complicated. In a typical polynomial, you only consider x square plus x cube, or let's say x to a large power, something 5, 7, 3, 4. We also have other terms like y and z something, right? However, this is the normal case, or just regular polynomials. Laurent polynomials are not much different. They just allow you to have negative coefficients on the top. Negative integers. Or you can just say all integers. That's better. All integers. Plus say x minus 3 plus x 5, 7, 3, 4 plus so on. Okay. So these are Laurent polynomials. And now seeing how this could seem much more complicated than this, because for example, you can't like if I simply had just this equation, let's say it's x to the power of minus 2. This is my p of x. And clearly I cannot let x equal to 0, right? Now, in a considerably more complicated equation like this, if I allow x equal to 0, then I get, in this situation, I get 1 by 0 square, which is clearly infinity. Or vaguely infinity, because there's a whole study on should we really be assigning everything to infinity, like 1 by 0 square or 1 by n square. And that's a whole topic on its own. That's why I'm going to say that. However, I just want you to notice that this case is much more difficult than this case. And so if I just tropicalize the whole thing, tropicalize it to like, heaven and back, I am going to get a much simpler thing, because these powers on the top simply become coefficients, negative coefficients. And this is why one of the applications over here is with Laurent polynomials. Next. Okay, so projective space is a whole topic of its own. We may not need to go into all that. Let's see what else is there. Projective tropical geometry we won't need. Tropical manifolds will be useful to us. Tropical manifolds and tropical curves. Tropical Jacobians will be a bit too much, so we will not be needing to get into that. However, the idea is that we will be applying mainly these two chapters on our minimization of neural networks. So let's start. I think I heard someone requesting to join. Doesn't pop up as usual. I see, someone's left. Okay, that's fine. Okay, so Right. So this is the part where we start reading, and the idea of it is like this, okay? We're all going to go turn by turn. We're all going to read it. For the initial parts of the reading, I'm going to be explaining the terms, but the goal is that eventually we should all be able to read at the same level. We should all be able to read it and understand it and provide comments about what kind of things we understand or what kind of things we were reminded of while reading such a thing. Okay? So, I'm going to go ahead and let's see how many people are left. We have Tanish, Utkarsh, Suhas. Alright, so let me just text the order. I'm just going to put it in the order I see. Utkarsh, Suhas, Tanish. Okay, so after I finish, I'm going to put Farhan after that. So immediately after me, Utkarsh is going to come, then Suhas, then Tanish. And this is how we are generally going to conduct most of our studies, okay? Are you guys comfortable with that?
Yeah.
Awesome. Okay. Cool. So first paragraph, we're going to go paragraph wise. The two words algebraic geometry may invoke different images for different people today. For some, it may be very abstract, even somewhat formalistic, adapted to the work in the most general setting possible. For many others, including the authors of this book, algebraic geometry is a branch of geometry in the first place. Geometry of spaces defined by polynomial equations. Go ahead, Utkarsh. Read the next paragraph.
Yeah, sure. So, note that unlike many algebraic properties, the resulting geometry depends not only on the type of the defining equations, but also on the choice of the numbers where we look for solutions. Okay.
I would like to add a comment about that.
Sorry?
I'd just like to add a comment about that.
Yeah,
okay.
Go ahead.
So, in fields like cryptography, if we have some sort of polynomial, x cubed plus, what is the general form of an elliptic? Minus yx plus something like that. Okay? There are different ways to approach this. We can either look for all real solutions, we can look for all rational solutions, or we can look for all integer solutions, integral solutions. So this would be real, this would be rational, and this would be integers. So when the author mentions this, right, where we look for solutions, this is what he means, okay? You can go ahead.
Yeah, the two most classical choices are the field R of real number and the field C of complex number. Both these fields come naturally enhanced with the so-called Euclidean topology, induced by the metric mod x minus y between 2 points, where x and y belongs to R or in C. Furthermore, real algebraic varieties are differentiable manifolds, perhaps with singularities, from a topological viewpoint, and complex algebraic varieties are a special kind of real algebraic varieties of twice the dimension.
Okay, so although there was a lot of jargon here, we don't need to understand all of it at all. So I'm just going to tell you some of the terms, or basically I'll just tell you the general message this guy is trying to say. Okay, so what he's saying is that by Euclidean topology we mean Euclidean space in some sense. So what does Euclidean space mean? I will see if I can draw that. But does anyone have a flat surface near you? If you could, just tell me if you're holding your flat surface, okay?
Yes.
Okay, so the distance between any 2 points on the flat surface that you are currently holding, okay, say this is my flat surface. The distance between any two of these points is given by what? Our friendly x1, okay, say this one is x1 comma y1, and say this one has x2 comma y2. So we have our friendly x1 minus x2 the whole square plus y1 minus y2 the whole square. Now this is the distance formula. More generally known as the Euclidean metric. Euclidean metric. Now, consider any non-flat surface near you. For example's sake, let's look at a ball. And let's consider the example that we are on Earth right now, yeah? Earth is a globe, clearly. However, if you look at your surroundings right now as a person just living in Bangalore, everything local to you seems to be flat.
Yeah, quite
right?
true.
So, when it comes to small distances, let's say we're zooming in like this. When it comes to small, when I zoom in completely or when I look at it locally, any two nearby points, let's say x comma y, and I calculate a distance between x comma y, it is going to be equal to my Euclidean metric or my distance formula. However, let me consider trying to draw the distance between these two. Now for me to calculate the distance, it's going to just directly cut through the diameter of the Earth, right? But the Earth has a surface and you cannot literally just go through the interior of the Earth to get to, say, the opposite side of the globe. What do? You instead travel along the surface of the Earth, which is, in this example, along the equator. So notice this. We are locally flat. However, we are globally not flat, clearly. What do we do to actually compute this distance? We start taking small steps. And like I said, locally they're flat, right? So I'm going to take steps of this size and I'm going to add them all up. At each point, I'm going to go slightly further, until what I look like looks sort of like this. Okay? Is everyone clear? That's a bad circle. Can I undo it? No, I cannot. Okay, tada. Anyways, so in this example, we're just summing up all, oh wow, okay. We're just summing up all the distances between xt to xt plus 1. And if we, make these gaps smaller and smaller, we'll eventually tend towards the integral from, say, x0 to xn. Let's say this final point is xn, this point is x0. So we're going to get an integral going from these points, x0, x, or let's just put xt, xt plus 1. So does that make sense to everyone so far? So just one point that I'd like to make, please do not confuse this with d of x from integration, okay? That's it. Besides that, if we're clear, we will conclude here because it's time for the next department. So any questions?
No, everything was
Okay.
No.
So a lot of this paragraph clearly seemed like a lot of jargon because these are all words that are well defined in higher math. Instead, I would just like to explain one of these words, which is a manifold, because I've already done right now. So what is a manifold? It is a surface that is locally flat. Okay, so in a sense, I've basically told you what a manifold is by showing you how we would typically calculate a distance from one point to another on a non-flat surface. So does this definition make sense to everyone?
Yes.
Awesome. So great job. Now you know what a manifold is, which most people don't, unless they've taken a math course. So yeah, this is a good start. next time onwards we will... I didn't realize, I think there's a lot of things that I didn't realize I need to teach, so I will choose a more basic book next time, because this is a very application oriented book, so we won't start from this directly. We'll start from another book called Gilbert and Strumfels. Right. Okay. This will be the book of our interest. Next class onwards, or next session onwards, let's not call it class because it's not a class. So next session onwards, we will be looking at this book and we'll read from this because it explains more, or at least this is the book I think will suit this session, the next session better than this book does. Okay, so thank you all